It's been 500 years since the first circumnavigation of the globe, and few could have predicted then that we'd be seeing detailed images of stars, galaxies, and exoplanets, like the ones produced by the James Webb Space Telescope this year. This month, we're looking at what these recent discoveries mean to our understanding of the universe. Why should we all know about distant galaxies? How will this learning impact us? And what role will artificial intelligence and machine learning play in the wider field of astronomy in the coming years? The questions are big, the area is even bigger, and we are delighted to be joined by two eminent fellows from the Royal Astronomical Society to review this expansive subject. This is Tessa Mathieson with the Oxford Comment. On today's episode, we are literally looking into space and discussing how the recent advances in astrophysics and astronomy and their techniques and instruments are teaching us more about the universe than ever before. For our first interview, we are delighted to welcome Claudia Maraston, Professor of Astrophysics at the University of Portsmouth. Claudia is an expert in theoretical astrophysics, in particular the calculation of theoretical spectra for stellar populations. She was awarded the 2018 Eddington Medal of the Royal Astronomical Society for her work of outstanding merit in theoretical astrophysics, and sits on the editorial board of the peer-reviewed scientific journal Monthly Notices of the Royal Astronomical Society. So today I'm speaking to Claudia Maraston. Claudia, would you like to introduce yourself?
Thank you, Tessa. Yes, as you said, I'm a professor of astrophysics. In particular, I specialize in studying the formation and evolution of galaxies from our local universe up to the dawn of time, as the James Webb Space Telescope is trying to unveil exactly at our times. The Royal Astronomical Society has played a fundamental role in my career. I've been awarded the Eddington Medal of the Royal Astronomical Society for my work in theoretical astrophysics, and that has really made a breakthrough in my careers. I'm very proud to say that I'm part of the scientific editors board of the Monthly Notices of the Royal Astronomical Society, which is one of the leading journals for astrophysics worldwide, and that I'm very proud to be on this board since 2018. I'm also a fellow of the Royal Astronomical Society and participate into events that are held in London, in Burlington House, but also all around the world when there are conferences supported. And currently, I teach 2 undergraduate courses at the 3rd and 4th year of Masters in Astrophysics at the University of Portsmouth. The 3rd year is called Modern Astrophysics and explain the physics of stars, galaxies, and black holes. The 4th year module is called Advanced Astrophysics, and there we discuss the major theories of galaxy formation in a cosmological context.
That's great, thank you. How would you explain astrophysics to someone who is new to the field?
Yes, so what I would say is that astrophysics is a most comprehensive and multidisciplinary science because by using all of the following, the laws of physics, mathematics, chemistry, and computing, aims at explaining the formation and evolution of the components of the cosmos, such as stars, galaxies, black holes, but also of the universe as a whole. Astrophysics is also in the best position to find out whether the known laws of physics as we know them and that have been probed on Earth are actually sufficient to explain the observed phenomena of the cosmos, or if new physics is needed to make sense of the grand picture. And this is exactly what happened. And after all, the cosmos is by far the most extreme laboratory that we can imagine.
Fantastic, thank you. Is the speed of light key to knowing and understanding astrophysics and its applications?
So the speed of light is really key. It enters the calculation of virtually every quantity in astrophysics. But let me start from our own star, from our parent star, the Sun. The energy of the Sun is calculated by using the famous Einstein equation, which converts matter into energy, and the proportionality is the speed of light to the square. If the speed of light changed, the energy from our star would change. And then galaxies emit light thanks to the billion of stars that they contain. And again, we use the speed of light as a fundamental ingredient to calculate the amount of energy and see structures in the universe. The speed of light is also crucial to understand how far in space and time structure and galaxies are located, exactly because the speed of light has a finite value. So all in all, we cannot do any astrophysics without the speed of light, and if that value would change, the whole astrophysics would be affected.
Thank you. So what is dark matter, and have we always known of its existence?
That's an excellent question. So dark matter is our way of explaining gravitational effects that we cannot associate to ordinary matter. Dark matter is something that we feel is there, but cannot be seen. Let me tell you, why is dark matter needed? Well, it was noticed that at the periphery of galaxies, where there is hardly any luminous star, yet the velocities of bodies in that darkness are high, as if there was some matter motivating and sustaining those velocities, but that matter is not associated to light. It happened 100 years ago that two astronomers provided the first indication and suggested that quite a sizable amount of matter could be in an invisible form. Ian Oort, in 1932, by analyzing the pattern of velocity in our own Milky Way, noticed that these velocities were high. Fritz Zwicky, in 1933, by analyzing a completely different environment, namely a large cluster of galaxies, which we call the Coma Galaxy, noticed that the energetics that he could associate to visible matter was insufficient to describe, again, the velocities of bodies in that cluster. But we need to acknowledge, to have completely firm this concept, an American scientist called Vera Rubin. She has analyzed all the spiral galaxies in the local universe and probed definitely that the velocities where the luminous matter is very low are high, as if there was something holding up this velocity. And it is thanks to Vera Rubin that we now, our generation, speaks about dark matter. But there is another problem, that is at the larger scales of the cosmos. After the Big Bang, when the universe is homogeneous and starts to expand, there is not enough matter to start forming galaxies. The matter that we can associate to normal things is insufficient to explain the formation of even our own Milky Way, and as a consequence also us. So without invoking as much as 30% in an invisible form, we would not be able to make galaxies as we know. So it is quite a dramatic and predominant intake. And I wish my generation would be able to finally understand what dark matter is.
Fantastic, thank you. Are there any key elements of astrophysics that we should all know about?
Yes, Tessa, I would say we should know the life cycle of our parent star. Our sun is 4.5 billion years old, and it is pretty much about halfway through its own life. So we have still 4.5 billions of years in front of us, after which the sun will first expand and become a red giant, for then shrinking down to the dimension of a white dwarf. This makes it such that the planetary system and life with it do not have an infinite lifespan in front of it, even if, when we speak about billions of years, naturally, this is much larger than anything we can imagine. Also, we should know that our sun will not end up as a black hole, but in fact as a universe white dwarf. The other thing I think we should know is what is our home galaxy and its place in the universe. We are positioned in the outskirts of a spiral arm of a normal spiral galaxy that is neither too big nor too small. It is really an ordinary spiral galaxy, as many others in the universe. We are not close to the central black hole, and we are also not in the far periphery of the galaxy. The other thing that I think we should know is how old is the universe, because this number is something that we astrophysicists determine with quite a good precision. And nowadays I can tell you that the universe is 13.67 billions of years old. And this means that it is quite ancient, but it has not always been there. We should also know that in 2022, we know quite accurately the major components of the universe, although 95% of it is actually unknown. And so we know that the universe is made by roughly 5% of baryons, so ordinary matter, stars, galaxies, gas, dust, planets, and human beings. But then roughly 30% of dark matter and roughly 70% of dark energy. These are the major components that we have now. And the other important things for us is to know where the elements, the chemical elements that are familiar to us, where do they come from? We should know that shortly after the Big Bang, the universe is able to make hydrogen and helium and a few other things really in traces. However, carbon, oxygen, magnesium, calcium, titanium, and all the rest come from the synthesis within stars. And finally, I would add that we should know that the universe is expanding, but in an accelerated mode. This turned out to be discovered a bit less than 20 years ago, and made a dramatic turn up in what we think is the destiny of the universe. As we know now, the accelerated expansion is progressing, and we are looking into a big rip as the final end of the universe.
Fantastic, thank you. It is said that the James Webb Space Telescope's cameras can look deep into space and far into the past. But what does this mean, and how does it do this?
So, from the equations of Einstein's of relativity, 100 years ago, it turned out something again radical and fundamental, that the space and time are actually connected, and time cannot be longer regarded as an absolute. And then came the speed of light that we discussed earlier. As light travels at a finite speed, and given the very large distances in the universe, that implies that when we collect the light from a distant object, that light will not testify of the object as it is now, but as it was when the light was emitted. In other words, the light transporting the information needs time to travel to us. Therefore, if we are able to collect the light emitted by distant objects at different distances, space-time distances in the cosmos, we can travel back in time. And that's why, in fact, the universe and astrophysics allow us to use time machines. And so, the other thing we know is that the universe expands, which implies that distant objects move away from us. And this is something we know that produces an effect that is a sort of Doppler effect, by which the frequencies of the emission of light, of the wavelengths, shift towards the red part of the spectrum, something known and called redshift. So why James Webb is going to be transformational? Because the James Webb Space Telescope has detectors that are sensitive to the red part of the spectrum. And therefore, the James Webb Space Telescope is able to capture the light that was emitted by the very primordial galaxies and stars whose light has traveled to us across the cosmic time and is now being captured in the red part of the spectrum. it was built exactly to the purpose of viewing the formation of the very first structure in the universe. Besides this, the James Webb is also bigger than what was the Hubble Space Telescope. And so it can collect more photons, and it collects just the right photons to allow us to look deep in space and far into the past.
Amazing, thank you. I feel like you might have answered this already, but we've seen the images the James Webb Space Telescope has given us of distant stars and galaxies in beautiful detail. Why is knowing more about distant galaxies important, and what does it teach us?
Yes, beautiful questions. Actually, we do not know yet the precise epoch at which stars and galaxies started to form. Yes, we discussed earlier, we certainly can have a precise dating of our own sun, but the sun is relatively young in the universe. But the very first generation of stars and galaxies happening shortly after the Big Bang in an epoch which we call Dark Ages, that is something we do not yet understand in detail, and it is crucial also an impact on our global cosmological view of the universe. In particular, something that I hope the James Webb Space Telescope will be able to probe, we are missing the very first generation of stars, the one that produced the first generation of chemical elements that we observe in the oldest stars in the Milky Way. The very ancient stars in the Milky Way show traces of iron, carbon, magnesium, a little bit, but not zero. And we are missing the previous generation of stars that have formed those elements. These are called population-free stars, and they should be shining shortly after the Big Bang. So all of these are mysteries that I cannot wait that the James Webb Space Telescope is going to tell us something about.
Great, thank you. What tools do you use in your day-to-day work, and how do you see them changing over the next 10 years?
So, as everyone knows, astrophysicists make abundant use of computing. That is due to the fact, it's due to multiple facts. First of all, we said it is a comprehensive topic, and therefore we need to include a lot of physics processes. Math, complicated or easy, but we need to include the equations to be solved. And also we need to include chemistry, and chemistry implies many elements and all the electrons. So the calculation we need to perform are quite demanding. And if I think about it, the astronomers of 30 years, 50 years ago were doing this with the technology of the time. Me, myself, I've noticed this strong evolution, for example, in the capability of computer. And right now, I calculate my models on supercomputers. We have one in this institute, and many institutes have those. This makes heavy calculation very fast, or let's say relatively fast. On the side of the observed data, modern telescopes actually inject a huge amount of data for billions and billions of galaxies. And this is going just to increase in the future. It's terabytes, it's petabytes, it's an incredible amount. It is right now impossible to perform a scientific analysis with low computing facilities. So, what can I see in the next 10 years? Well, we are promised that there will be quantum computing. Quantum computing is one of those things that should actually resolve most of our problem in terms of heavy computation. I personally don't think a computer can substitute our brains and minds, not even in the form of artificial intelligence, but quantum computing should be able to tackle problems that are far too complex because of the many variables and the many processes for normal computer nowadays. So I think this is the major revolution that may happen in the next 10 years in the tools that I'm using in my everyday research.
Thank you. You were awarded the Royal Astronomical Society's Eddington Medal in 2018 for your work in theoretical astrophysics, and are on the editorial board for the monthly notices of the Royal Astronomical Society journal since 2018 also. What role does the RAS and MNRIS play in furthering or promoting the importance of academic research in this area?
So the RAS, I would call it as an historical and also fundamental club of passion. It's really passion gluing people together, testifying and celebrating astrophysics, the people around it, and the discoveries since about 2 centuries. It's really a piece of history we cannot live without. The RAS collects academics, but also amateurs, everyone with an interest in space, and pays much attention to inclusivity and diversity. And the monthly notice is at the peak of the quality publication for scientific journal. It's one of the leading astronomical journals. It was founded nearly 200 years ago, so it is really the oldest, the most historical with the past. For example, it is on the monthly notices that the fundamental papers by Arthur Eddington were published in 1920, and so I'm coming to the Eddington Medal. Arthur Eddington published this paper suggesting the source of the energy of the sun was indeed nuclear fusion, well before those equations were written clearly. And in the same paper, he would advocate the use of the same energy to support the needs, the energetic needs of our planet. And how timely are this paper exactly in the current situation? Those are beautiful papers that I strongly recommend everyone to read. And so it was really, being myself a great fond of the clearness and creative mind of Arthur Eddington, the award of the Eddington Medal really, as you say, made my day. It changed my life really forever, because it gave me a sense of accomplishment and satisfaction in my profession. And I often go and look at the Eddington, my medal, and I hold it in my hand, and it gives me motivation to go. So it was the medal I always wanted to get, and so I'm quite satisfied that this has happened. In the same year, as you said, I was honored to be invited to join the board of the editor of the monthly notices. But the work that I was able to engage with is going really beyond my expectation. First of all, the board of scientific editors, assistant editors, the chief editor, and all the publisher makes a superb work environment where we all conversate and exchange opinion in a really great atmosphere, I need to say. But also, having published for 20 years in the same journal, now I can see the new generation coming out with new publication, and especially I keep touch with the latest discoveries and the latest opinion, and I can actually make myself informed and keep myself informed every day. I can tell you that still, when I get a paper assigned to me, I avidly open it and read the abstract because I want to know what's new. So being an editor is a fantastic side of my profession.
Thank you. So final question from me. It feels like astrophysics is an area that will see much more growth to come in the future. What careers are available now to students of astrophysics? And do you see any specific growth areas for the future?
Yes, very good question. Certainly much different from my generation, where we thought that we study astrophysics and we will become an astronomer. And we had the image of the astronomers on top of mountains looking at the telescopes. In reality, students of astrophysics have really plenty of opportunities because the discipline is so comprehensive and open-minded. The study is challenging, and the tools we use are the most sophisticated ones, for the simple reason that we have to deal with big data and large computer simulation. Our students at the end are of a unique, special sort. So the available careers are naturally the academic ones, but also research positions in industry in various fields where I see our students competing and winning positions over other type of degrees. And these fields span naturally data science, which is really nowadays much in vogue, climate research, energy research, and space technology. I would also add career in government and public services, exactly because of the link between climate and global politics and the background in astrophysics. Also, certainly thanks to the development of the past 2 decades in which the RAS played a fundamental role, science communication, media, and public engagement is now a natural career opportunity for a degree in astrophysics. Last and not least, teaching in secondary school and preparing and motivate the next generation of scientists is something I would say students of astrophysics can do at best. Regarding the growth areas that you mentioned, data science, artificial intelligence, and quantum computing are the things we are discussing right now. And I think the students will have a future with those.
Well, thank you so much, Claudia, for joining us today on the Oxford Common. It's been absolutely fascinating hearing kind of your day-to-day insight into being an editor, big conversations on dark matter, the speed of light, and the James Webb Telescope. So thank you so much for joining us today.
Thank you, Tessa.
Our next guest is Jonathan Tennyson, Massey Professor of Physics at University College London. Jonathan's research specialises in the accurate quantum mechanical treatments of both the spectroscopy and collision properties of small molecules, with an emphasis on the provision of data of other research areas. He is editor-in-chief of the open access peer-reviewed scientific journal, the Royal Astronomical Society Techniques and Instruments. So today I'm interviewing Jonathan Tennyson, who is editor-in-chief of the Royal Astronomical Society Techniques and Instruments journal. Jonathan, would you like to introduce yourself?
Hi, yes, I'm Jonathan Tennyson. So my day job is that I'm Massey Professor of Physics at University College London. And as Tessa just said, I'm editor-in-chief in this new journal called RASTI for short.
Fantastic, thank you. So it's been 500 years since the circumnavigation of the globe, and here we are today with a range of instruments that can teach us much more than ever before, far beyond our own planet. Can you give us a brief introduction to the key instruments used in astronomy and geophysics today and what they do?
So that's a very broad question because there are a lot of them. Starting top down, we have a number of space instruments flying up there. James Webb Telescope, which I'm sure we'll come to, being a famous current advance example, but there are probably 8 to 10 astronomical observing missions, taking data from around the universe with different objectives. There are also missions flying to other planets. You've a lot of publicity of rovers on Mars and things like that, but there are a lot of interplanetary space missions within the solar system, maybe about 5 or 6 of those. Then if you turn to the geophysics, you also get a load of space instruments. They just look the other way. So they look down, they do things like monitor the size of the Earth's ice cap. Carbon dioxide in the air is a major and other atmospheric components. That's a major activity on spaceborne missions. So you get a whole variety of space missions which are looking at other worlds or our own world, trying to take the advantage of taking the view from space. On the ground, of course, we have telescopes looking out at the night skies. That goes back, that was already happening 500 years ago, though I was trying in my head to calculate how long ago it was since Galileo invented the telescope, and you start to be able to do this accurately. It's slightly less than 500 years. It's about 470 or something. There are a lot of ground-based observatories or ground-based observatories going back to China 2,000 years ago, actually. But they've got very high resolution, also using lots of telescopes altogether to get very fine positional detail. So there's a big variety of those going on. And similarly for geophysics, because we're doing our own Earth, clearly there are all sorts of measurements. I mean, take seismometers, for instance, looking at seismology and earthquakes on the Earth and a whole variety of things. So I think the whole range of scientific measurements one can make in both astrophysics and geophysics, or astronomy and geophysics, is now very broad, and it's very difficult to list them all without becoming extremely boring and just going into list mode.
Thank you very much. So we've seen and heard a lot about the James Webb Space Telescope recently and admired the stunning images it has produced. But what exactly can it show us, and how will this data be used?
So again, James Webb is a very versatile instrument. So it's like Hubble Space Telescope. It's designed as a general telescope. So there is no single answer to your question. It'll be used for a lot of different things. So it was originally conceived and designed to see very, very faint objects very far away. And indeed, it's doing that. It's probing the earliest galaxies and even slightly beyond when these galaxies were slightly earlier than when these galaxies are formed, back to the very, very origins of the universe. So we will learn about how the universe formed, and we're talking, the universe is about 14.5 billion years old, so we're talking 13 billion years ago and older. So that was the sort of main original objective of JWST, but because it's very versatile, you're going to look at an awful lot of other things. And my personal interests, I'm very keen on actually discovering these new worlds that we found orbiting around other stars called exoplanets. And James Webb is already beginning to take unique spectra, actually looking at the light of different colors of these exoplanet objects. They've already detected very clear signs of water on one planet and carbon dioxide on another planet. And as I speak to you, I'm sitting here in anticipation of the first full early data release of these things, which I think is going to come up shortly, maybe later on in this year. And I think we're going to learn a lot of information from looking at these planets. But James Webb will look at an awful lot of other objects as well. And what James Webb has is the ability to see at very nice resolution the colors of light in infrared. So infrared is slightly cooler than the visible wavelengths we see in our eyes, and you can look at slightly cooler objects this way. And there are a lot of these in space, and it's going to be it is by some distance the best infrared capable telescope we've had in space, and it's the first one we've had for a while. So there's a lot of questions astronomers want to know answers to.
Thank you very much. So what is multi-messenger astronomy?
So astronomy sort of goes in phases. The original phase, which I talked about with Galileo and the Chinese, you just looked at the night sky, like with our naked eye or with help of telescopes to get better, and then you're just looking at the visible light. As people have got better and started being able to divide light into its constituent colors, so in the visible light in the colors of the rainbow, and then in the other wavelengths as well, you get lots of different information from the sort of light you're looking at, everything from very energetic radiation as represented by X-rays, right the way down to the microwave, the sort of thing you use in your microwave cookers, which are very long wavelength, low energy radiation. So that's sort of the building blocks of astronomy, and you learn an awful lot from analyzing that very carefully. But then we've had two other forms of information that we can get. Going back a few years now, 20, 30 years, we've begun to look at neutrinos, which are strange subatomic particles that basically penetrate everything. So they're very difficult to stop. But stars, when they die, for instance, and undergo supernova explosions, they release huge bursts of neutrinos. And actually, I can tell you exactly when this started, because a neutrino, a supernova exploded in 1987, released a burst of neutrinos, and they were observed on Earth. So that started neutrino astronomy, which is a second type of message you can get beyond light from the stars. And then much more recently, people have detected gravitational waves, which is caused by very massive objects, particularly things like black holes interacting with each other or with other objects. And they, in the concepts of Einstein, they warp space-time in a strange way and leave off waves which are extremely difficult to detect. It took us many, many years of perfecting it to be able to detect these things, but now people are finding out some really interesting things looking at gravitational waves. For instance, they've already rethought the way that heavy elements that are heavier than ions, things like lead and gold and uranium, are formed in the stars, because they've realized there are a certain form of collisions between stars that can produce these elements that hadn't been thought about until they started looking at the gravitational waves caused by these stars.
Thank you. With the highly technical and specialized techniques and instruments in the field, how do we keep up with all the data out there and ensure we learn as much as we can from it? Where is it all stored?
So firstly, it's difficult to keep up with everything. Even as a practicing scientist, there's so much going on that one tends to keep up with one's own speciality. There are repositories where people keep data. The astronomers have in many ways pioneered the whole open data revolution, which is now becoming very common in all sorts of walks of certainly academic life, the idea that you give away your data. But the astronomers have always been very good at this. There's something, for instance, called the Virtual Observatory, which stores observational data collected from telescopes from the stars. So you can go back and look at, for instance, if you look at an object and think it's changed, it looks different this year, you can go back and see if someone took a recording of what it looked like 10 years ago and see whether it has changed. So the Virtual Observatory is a major data source, but then there are all sorts of other data banks. And indeed, we're just opening a new telescope called the Square Kilometre Array, which is going to be split between South Africa and Australia. And this is going to produce as much data as the whole internet was doing about 15 years ago. So storing that data is going to be a huge challenge and something that people are working on very hard. It will have its own private repository. James Webb Telescope, as you said, is very much under an open data policy. The data is made available to people as early as possible, but that's again being stored in a specialist archive put together by the institute that's running the telescope. So the answer is there are quite a variety of different data repositories, but there is a big commitment to making the data as widely available and usable as possible.
Yeah, that's a lot of data. Which technique has given us the biggest advancement to where we are today?
I'm a big fan of a technique called spectroscopy, and spectroscopy involves separating the light into its colors, so you get a lot of individual information as a function of the color of the light. So if you go back 200 or so years, astronomers found a way of measuring the distance to the stars around us using so-called parallax. What they did was to take a position of the star and then 6 months later retake the position, and knowing the orbit of the Earth around the sun, they could measure the distance to the star they were looking at, and they were shocked. They were really shocked at the result because the stars were so far away. Now, we all know that now because it's become part of our culture, but at the time it was very surprising. And a logical positive philosopher called Auguste Comte made an interesting pronouncement. We would never know what the stars were made of because we were thinking they were so far away we'd never get there. This turns out to be completely wrong, because using spectroscopy we can analyze the light from the stars in exquisite detail and work out the atomic composition of the stars to very fine level of accuracy. So the result is we actually know much more about the composition of stars on the other side of our galaxy than we know about the center of our own Earth, for which we can't do spectroscopy. So it's very interesting that we can look at the universe around us as this exquisite detail and find out things actually we don't know about the Earth we're standing on.
Thank you. Where do you see the future for artificial intelligence and machine learning in the wider astronomy field?
So machine learning is already widely being used in astronomy. So to give you an example, one of my colleagues was very heavily involved in a project called DESI, Dark Energy Survey, and this took spectra, so the colors of light from many millions of galaxies, and each of those galaxies is a treasure mine of information, but that's too much information for one person to go and look through. So you get your machines to go through and mine it and build up pictures, find out the outliers, pick up the norm. That sort of activity, as the amount of data we get coming in is increasing, that sort of activity is just going to increase and increase and increase, because the sort of volumes of data I already mentioned with SKA, for example, are simply too much for human beings to pick over piece by piece. So you need all the help you can get from machines who can do the work for you, can fit things, can understand things, can parameterize things. So it's already being very widely used in astronomy and geophysics, and I'm sure it will continue to be used even more so that way.
Fantastic, thank you. As part of the Transform to Open Science, or TOPS program, NASA has declared 2023 to be the year of open science. What is open science?
So there's long been, or fairly long been, something called open data, which is called fair data, which means findable, accessible, interoperable, and reproducible. And the idea is that science should not just be correct, it should be shown to be correct, and other people can redo your results, reproduce them. Otherwise, we don't really know what is being done is correct. And the whole TOPS concept is not just to make that for data, to make that to all aspects of science. And in fact, the journal that I've helped launch this year, RASTI, is very much dedicated to fulfilling that agenda, because a lot of journals, what they're dedicated to is carrying very exciting scientific results, and clearly that's very important. but sometimes justifying exactly all the steps that go to make that result, either how you built the instruments or the computer codes you ran or the data, the machine learning algorithms you're running. These things are very complicated all in their own right. And what we want to do is capture all that so that people can actually completely reproduce all results. And I think it's extremely important you go down this route as science gets bigger and bigger, underpinning nearly all activities of society. It also gets more specialized. You have to take a lot on trust that what people are doing is correct, and you want to make sure that you really can prove it's correct. So if you get some result that seems somehow odd or not quite believable, you can go where you can reproduce it, you can check it's correct. And this is an important part of the scientific method. So this idea of having this TOPS program absolutely has my full support.
That's great, thank you. So who is leading the race in astronomy and geophysics? Are there any regions that show increased activity, unexpected, or big advances?
So up until maybe 5 years ago, there were essentially NASA, the European Space Agency, probably JAXA in Japan. And then suddenly over the last few years, there's been a whole outburst of other countries with space agencies doing space missions. Particularly active is China, who have some very interesting space missions. They've also built some really world-leading telescopes, so that if you're going to say who is coming up very fast, one has to say China to start off with, and that's probably true if you'd asked me the same question about a lot of other scientific areas as well, because they're putting a tremendous investment into science. They have a lot of talented scientists, and they're clearly becoming major world players. But an awful lot of other countries are also getting into the space race. So Saudi Arabia, India, I don't want to name them all because I won't list them all, but there actually been a big plethora of people launching space missions for the first time in the last 5 years. So it's become much more widespread to have space activity and just get involved in the whole use of space for looking at astronomy. If I can, for the moment, personalize it a bit, I'm actually involved with a company called Blue Sky Space, who are actually trying to launch space missions, which you then sell telescope time either as part of a team doing a survey or as individuals, to actually basically democratize space activity so that anybody can participate. You don't have to be a shareholder in a company with a major space agency.
Perfect, thank you. And finally, what do you feel the early career researchers of today might be studying 25 years from now?
So I hope 25 years from now, just talking about my personal favorite topic in astrophysics is exoplanets. I think 25 years from now, I hope we will have discovered planets which not only are habitable, that show signs of having life on them. And I hope that we'll actually be beginnings of studying maybe versions of the early Earth or even late Earth with different stages of civilizations and different stages of life on it. I mean, I think that's a fascinating topic, which will really capture people outside the scientific area in terms of what it means in the public. Now, that is one area. We still have lots of unanswered questions about how the universe started, how that links to fundamental particle physics and the fundamentals of our of the whole makeup of the worlds as we know it, matter and everything. And I'm sure that will be an enduring study. There's been a huge amount of progress made on that in my life in science. I've watched from when everything was theoretical to now it's actually a lot of observational work. And the theories, some of which have proved to be correct, some of which haven't, are now underpinned by hard observation. I think that will also go a lot further in the next 20, 25 years. And of course, the James Webb Telescope is underpinning a lot of those advances on both sides. I don't think James Webb will discover a planet which firmly has life on it, but it may give us some pointers in that direction. It will help us look deeper into the universe.
What kind of pointers of life could that include?
So there's a whole discussion of on a topic which is called biosignatures, which how you detect life. And if I take this back to its very basics, there was an American planetary astronomer, Carl Sagan, who's died something like 25 years ago, was very imaginative. And one of the things he got NASA to do when the Galileo mission was going to Jupiter in the very late 1970s was to turn all the instruments on Galileo back on Earth and say, if we look at Earth from a long distance away, how do we can tell there's life on it? And the answer, I mean, now is accepted, but I think at the time was quite surprising. was that they saw a lot of methane in the Earth's atmosphere, which, as you know, is full of oxygen. Oxygen should oxidize methane very quickly. They saw methane 10 to the power of 100 outside thermodynamic equilibrium. That meant that there was something on the Earth's surface producing large quantities of methane all the time, and that had to be life. Or in the very delicate words of the Nature article that published this was caused by flatulent rumanoids. In rather more simple English, it's cows farting. So looking for these sort of non-equilibrium behavior in atmosphere is the first sign. Oxygen and methane is a clear one, because if you're looking at Earth 2.0, I think one of the problems of searching for life is trying to extrapolate from one example. So we have one planet which is teeming with life. We know that life is very pervasive. It grows, obviously, what we can see, but also under Arctic night shelves, in volcanoes, all sorts of places which you think were bottom of the ocean, all sorts of places you think may be hostile to life. So it seems quite likely it may form other places, but it may look very different. So you have to be a little bit imaginative of how you're going to do this. But I think the first thing is actually looking for atmospheres that are quite clearly outside equilibrium in some way that is very difficult to explain just in terms of geology and lightning and other natural processes that one might get. Once you've got that, then you begin looking for the other things. If you want my personal opinion on this, the wrong way of doing this is going about looking for so-called intelligent life, SETI type things, so looking for radio waves and things like this. Because if you look at Earth, I date the observation of intelligent life on Earth from when Marconi originally put radio waves into the upper atmosphere, which is about 1890. Yet the Earth is 4.5 billion years old. So we're talking 120 years out of 4 billion years. It's a pretty poor ratio statistically. In that 4 billion years, probably there were other signs of life for half that time, 2.5 billion years. So you're much better looking for the 2.5 billion years ratio for the what I call is the search for extraterrestrial unintelligence. And then once you've got that, then you can ask questions. Then you can say, is this planet giving out radio waves? Is other things happening? But I think the first thing you want to do is identify places of interest that may have life on them.
That's great. Thank you so much. Well, thank you so much for joining us today, Jonathan. That was absolutely fascinating. It's been an absolute pleasure speaking to you today.
Okay, thank you.
We would like to thank Professor Claudia Maraston and Professor Jonathan Tennyson for joining us on today's episode. Please check out our show notes on the OUP blog for a recommended reading list exploring just a few of the topics we discussed today. This is the last episode of the Oxford Comment in 2022. We will be back with a new episode on the last Tuesday of January 2023. In the meantime, be sure to follow Oxford Academic on Facebook, Twitter, SoundCloud and YouTube, and please do subscribe to the Oxford Comment wherever you regularly listen to podcasts, including Apple, Google and Spotify. Lastly, we want to thank the crew of the Oxford Comment for their assistance on today's episode. Episode 78 was produced by Filippi and Himalee Rupesinghe. This is Tessa Mathieson. Thank you for listening.